Okay. So, okay. So today we will see how uh, we learned about the DTRs, which is the transformer-based object detector previously. So today we will see more advanced version of the DTR today. Okay. So this is the DTR architecture previously that we learned. Okay. So I mean, different to the original transformer, our input to the transformer, their encoder and decoder is the image feature extracted from ResNet. Okay. And this is the encoder and this is the decoder. And here, the core operation in transformer is the attention mechanism. So by transforming the input to this transformer into the value key queries, okay, and by applying the attention mechanism, and also we will apply the positional encoding. We will add that positional encoding to the key and query values and apply the attention mechanism. And we will call that as the self-attention because all of the input to that attention is coming from the same signal. Okay. And here in encoder, we are having improved feature. Okay. So in DETR, we can interpret the feature obtained from the output of the encoder as the enhanced feature. Okay, so we already inputting the image feature extracted from ResNet and then apply the self-attention mechanism to enhance the image feature. And also in the decoder, there are object queries, but differently to the text, the natural language processing domain, and we don't have any sequence meaning in this decoder input. Okay, and also we don't have any semantic meaning yet for these object queries, but this is some in the DTR architecture. This is some vector, d-dimensional vector which is applied with self-attention first, and then attended with cross-attention by cross-attending with the image features that we obtain from the encoder output. Uh, the, I mean, this object query enhanced feature is used as the queries to the cross-attention mechanism, and they are further mapped to bounding box and the class information in the DETR architecture. Okay. So this is the original DETR architecture we have learned, and this is published in ECCB 2020. Okay. And these object queries are not having any semantic meaning yet, but they are updated during the training process to maximize the accuracy of this class prediction and the bounding box prediction. Okay. After the training, these object queries are updated to maximize the accuracy of class prediction and bounding box prediction, but still they are not having any semantic meanings yet. Okay. So later research is tackling the several aspects of the weaknesses in the DETR, but mostly they are saying that DETR architecture, they are slow to train. Okay? So it takes a lot of efforts to properly train this DETR. Okay, so compared to the fast RCNN architecture, which is the CNN baseline for the object detection, it takes 10 to 20 times during the training. Okay. And also, even with this training time, they are not that effective for detecting the small object. Okay. And uh, so for capturing small and large objects simultaneously, we may have to use some multi-scale feature extractor. So if we extract the 2D features from the large images at the same time with the small rescaled images, then the ability to detect the small object that is enhanced. But the thing is, if we involve multi-scale features in the DETR architecture, then DETR already takes a lot of resources, but extending the DETR in multi-scales, that will take also a lot of resources. Okay, so that is somehow dilemma in developing the DETR. And also attention mechanism in the transformer. When their input to the transformer, there are n number of tokens, then the attention architecture, okay, attention mechanism, basically their time complexity is order n square. Okay, so it requires quadratic computation with respect to the pixel numbers, which is the number of tokens in attention mechanism. So this is the problem of the DTR. There are some scaling problem. We want to involve multi-scale feature extractor, but extending DTR to the multi-scales, it takes a lot of complexity. And also attention mechanism by nature, its time complexity is quadratic. So the deformable attention mechanism is proposed to reduce the complexity of the attention mechanism in the vision domain. So we call that as the deformable attention. And we will call the DETR architecture that is having this deformable attention as the deformable DETR. Okay. So the original DETR is published in ECCB 20, and this deformable DETR is published in ICLR 21. Okay. And their motivation is they are wanting to reduce the complexity of the attention mechanism, which has the quadratic complexity, to have the linear complexity. And then they are involving multi-scale feature maps to capture both large scale and small scale objects. Okay? By reducing the complexity of attention mechanism, they are involving instead they are involving multi-scale needs in their feature encoder. um, so this is the original attention mechanism we have learned. Okay, so there are key query values uh, involved. Okay, so basically using key and query, we are somehow measuring the similarity between the tokens, and then applying softmax, we are converting that into the weight, and then multiply with the value feature. Okay, and this is how the attention mechanism is calculated. Okay, and also if we use multiple head for the attention mechanism, then multiple head, their representation is concatenated, and another weight term, the linear term, is multiplied to convert that into some other vector. So this is the multi-head attention. And we can reformulate this same operation into this. Okay, so this is kind of the weight matrix. So this part, the key query multiplication, we can interpret that as the weight. Okay, and A matrix, we can think of that having some weight between key and query. Okay, And also there are m number of multi-head. So this is for multi-head, okay? And this is the key query weight, and this is the value vector, okay? So for the value vector, we are multiplying some weight for the low value query, uh, low value vector, and then summing them over the weight, okay? And multiply another weight for the multi-head, okay? And also, this is how to say, how we define the values, okay? So because uh, in detail, the feature space is in the two-dimensional space. So this omega is actually denoting some pixels in the feature map, 2D feature map, okay? So this K is denoting some dense, how to say, sorry. Okay. So this omega k is normally defined as all of the nearby, I mean, all of the pixels in the images. Okay. So k is belonging to omega k, and omega k is normally denoting all the pixels in the 2D feature map. Okay. So actually, we are multiplying all of the feature, we are considering all of the 2D feature map, their pixels, and calculating the similarity between that pixel and all other dense relationship with the other pixels. We are calculating the new features. That's the original attention mechanism. And thing is, in the deformable detail, for calculating this A matrix, which is the measuring the similarity between key and query, uh, the idea of this deformable DTR is they are wanting to replace this to the linear equation, not as the quadratic function like multiplying Q and query, key and query as the previous attention mechanism, but instead they are wanting to infer this A and QK from applying some linear operation to the queries, okay? Not applying, not densely considering the relationship between other queries. They are wanting to estimate this A matrix, which is the similarity between two input, two tokens, okay? And then they are wanting to multiply the value vectors, okay? So here is the derivation for this new deformable attention mechanism. So this is the multi-head attention mechanism that we learned, okay? So this is actually uh, this formula, and you can interpret this as this. So these two are in the same form. They are denoting the same thing. But in the deformable attention mechanism, what has been changed is uh, this x of k is not anymore the dense pixel values in the 2D feature map, but instead they will now, how to say, consider only K candidate vector, okay? K candidate value vector instead of the dense vectors inherent in the 2D feature map. So previously, this omega K is denoting all the dense pixels in the 2D feature map. But now we are changing that to have some of the K pixels, okay, K nearby pixels, okay. So things are a lot simplified thanks to this change. Okay, previously there are dense feature map was considered for the K, but now we will consider only sparse number of pixels. Okay, for this X. Okay, and also which pixels will be considered is decided by these offsets. Okay, so we will only, for example, count K is normally 3 to 5. Okay, only will 3 to 5 nearby pixels rather than considering all the dense nearby pixels. And we will estimate their offsets. Okay, 무슨 소리예요? 아, 공사하나? Okay, so now we will estimate some offsets from query vector, some query pixels, and then for that location, we will get the 2D feature values, okay? Not considering all the dense 2D feature pixels, we will consider only how to say, value vectors, which is nearby to the query pixels, okay? And now, when calculating this attention, this, I mean, and also another changes are made here, sorry. So previously, when calculating this A matrix, we explicitly apply this type of multiplication between query and K matrix. But here, when calculating this A matrix that measures the contribution of this feature, we estimate this by applying some linear operation to the query pixel features. Okay? So this is another difference made to the deformable attention mechanism. So now, previously, when calculating A matrix, there requires quadratic complexity because we are multiplying all the key and all the queries, okay? And also we are considering all the pixels, dense pixels in the 2D feature as the value vector. But in the deformable attention, we are considering only the nearby 3 to 5 pixels as the value vector. And also when calculating the weight of this vector, we apply the linear operation instead of quadratic multiplication. So because of that, this deformable attention is becoming a lot simpler. And this is the multi-scale extension of this deformable attention mechanism, which means multi-scale. MS means the multi-scale. Okay, as I mentioned previously, to capture both small-scale object and large-scale object, we may require multi-scale feature map. So previously in X, that's denoting the coordinate for one scale feature map. But now we are extracting multi-scale feature having L levels of feature. And this X over L is denoting pixel coordinate for that L level of feature. Okay. And we are having one more iteration for that L level now. Okay. So, but besides that, everything is same as the original deformable attention. Okay. So now this thing is happening like this. So we are reducing the complexity of the multi-head attention mechanism by reducing the number of vectors and the complexity of the attention mechanism by actually replacing this quadratic multiplication to the linear operation. Okay, and instead we are involving more feature scales. Okay, so now we have the multi-scale deformable attention mechanism. Okay, so this is showing, I mean, the the deformable attention here. So this is the query feature. Query feature. Sorry. So the query feature means in two-dimensional feature map. This is the 2D feature map. We need to how to say pointing one location, and that location's feature is called as the query feature. And actually, that coordinate is referred as the reference point. Okay, so this PQ is denoting the reference position of the query, and query feature G of Q is denoting that location's feature. And from the G of Q, which is the query feature, we are estimating delta P MQK, and also by applying linear operation, we are estimating attention weight. Okay, so that's actually coincides to my previous explanation. So now here, this delta Q is estimated from Z of Q, which is the query feature. And also this AMQK is also estimated from this query feature, okay? Not not doing multiplication between query and key. We are directly estimating this weight and also this offset of the pixels directly from the query feature. So all the operation now is becoming linear, okay? And in this 2D feature map, this was the reference point, but by applying this delta P MQK in multiple head, this delta P is differently obtained, and we can get this, how to say, value features. We can select 3 to 5 value features by applying this delta P, okay? And then we already also calculate this A matrix, which is the contribution of this value feature. And then now we can get each head attention value. And by applying another weight to concatenate the multi-head, okay, output and get the final outputs here. Okay, that's the deformable attention mechanism. Okay. Okay, so I will maybe have to explain this further after this slide. Okay. And also in the deformable DTR, the bounding box information was, how to say, the low coordinate of their center position and their width and height. Their width and height was estimated from the DTR's head. Okay, their low coordinate values are of course, they are normalized, but their low values are estimated from the head of the DETR previously. But uh, now somehow we are having some previous in the how to say I have to say this reference point. This reference point is meaning how to say the initial estimation for the bounding box. They are uh, I mean in the deformable detail, they formulate their bounding box estimation uh, by applying inverse of sigma to previous layers estimations and then apply addition for these layers output. Okay, so for each layer, they are only estimating the residual component of the bounding box information, and by applying inverse sigmoid to previous layers bounding box information, and then apply by doing addition to residual and previous layers bounding box information, and then apply another sigmoid operation here. Okay, so by doing this, they can make the overall process more stable. So they only, how to say, estimate the residuals, not the low coordinate bounding boxes themselves. Okay. And also this iterative bounding box refinement, they are happening during, how to say, decoding process. Okay. So here in the decoder, there are multiple cross-attention steps. So in here, in each step, they are estimating the bounding box and estimating only the residuals and applying inverse sigmoid to previous layers output and add this residual and apply the sigmoid regarding that as the new bounding box estimation. And another important thing that have been made in the deformable DTR is um, so actually if there's no part here, then that is actually same as the encoder decoder architecture that we have learned. Okay, so I mean the transformers are composed of encoder decoder architecture. And initially, image features are enhanced, and that's cross-attended with object query enhanced feature in the decoder and output the class information and the bounding box information. That's the original DTR. But once I told that the object queries, that's problem because they are not having any semantic meaning. So here, the output of the DTR had to be bounding box information and also the class information. But here, encoder part, that's we call that as the enhanced image feature. Okay. But we are cross-attending this enhanced image feature with some random, anyways, meaningless object queries, okay, to output this class information and bounding box information. So some people say that these object queries, which is the decoder input, are irrelevant to the input images. So because of this, irrelevancy to the input images, they are making the overall DTR training slow. For example, if we can give some of the image information to this object query, okay, the assumption is if we can give some image information to these object queries, mapping to this class information and bounding box information might be accelerated. Okay, that was the original assumption. And instead of how to say use the object queries learned from decoding process, this two-stage deformable DTR, what they are doing is they are estimating additional output to the encoder part and use that as the object queries. Okay, that is the two-stage deformable DTR variant. And now the object queries are becoming relevant to the input images because this is the image feature, and encoder, we are somehow enhancing the image feature, and then we are inputting this to the decoder's input. Okay. So in deformable DTR, by doing this two-stage deformable DTR, somehow we can give some image relevant information to the object query and thereby increasing the accuracy. So here, this is the original deformable DTR, and this is the iterative bounding box information scheme and two-stage deformable DTR scheme. So you can see there has been some accuracy improvement by doing this type of things. And also, compared to the original DTR, original maybe DTR, okay, they are requiring 10 times epochs compared to the deformable DTR, only taking 50 epochs, okay? But still, deformable DTR, they are getting better performance than DTR. And this is showing some DTR architecture trained only for the 50 epochs. And you can feel that this original DTR with less number of training epochs are inferior to the deformable DTR with the same epochs. So this is AP, which is the accuracy, and higher is better. Okay, so you can feel like that. And compared to the faster CNN that takes 109 epochs to be how to say converged. Compared to that, DTR still takes 5 times more epochs to be converged, but deformable DTR it has half number of epochs to be converged and also producing better accuracy compared to the fast RCNN. Okay. So in the deformable DTR, the important changes has been made for the attention mechanism by replacing the quadratic complexity to the linear operation and reduce the number of value vector, okay, by estimating actually the offsets to the nearby pixels, okay, and then scaling up their uh, feature into the multi-scale and thereby of making the training process fast and also increase the accuracy, okay, and give the ability to capture both small scale and large scale objects. And also they are applying this iterative bounding box refinement and two-stage deformable DTR to further increase the accuracy. And that is the deformable DTR. And also there has been some more important changes by proposing this conditional DTR. So these approaches are more actively, how to say, research for the meaningless, improving the meaningless object queries. Okay, so in deformable DTR, they are considering that using this two-stage DTR architecture, but mostly they are changing, how to say, the attention mechanism to the linear mechanism. That was the main contribution of the deformable DTR. But this conditional DTR, they are wanting to explicitly give some spatial information to the object queries and experiment if that can improve the training property of the DTR. So the problem the paper mentioning is samely as the deformable DTR, the slow convergence speed of the DTR was the problem. And this is the DTR trained for 50 epochs. And this is the DTR's result trained for 500 epochs. Okay, when trained with 500 epochs, DTR becoming to estimate 4 extremas in the bounding box. Okay, so these yellow signals are somehow capturing the DTR's outputs, capturing the extremas of the bounding boxes. So here the upper extrema, and this is capturing the bottom extrema, left, right. These figures are denoting. So when DTR is trained over 500 epochs, they are well capturing the extrema of the bounding boxes. But if DTR is trained only for the 50 epochs, they are somehow not well capturing this extrema of the bounding boxes. But in the conditional DTR, using only 50 epochs, they are becoming to capture these 4 extrema values of the bounding boxes. That's what they are telling about, okay? So somehow this conditional DTR is also saying that they can accelerate the training of the DTR by explicitly giving some spatial meaning to the object query. Okay, so object queries are not using any image-specific information while offering only attention wave map. Okay, in previous DTR. So it was hard for the DTR to map object queries to bounding box information and also both for bounding boxes and also the class information. So they are assuming that that was the main cause for slow convergence of the DTR. So here, in the conditional DTR, they are wanting to involve this right part. And this part, what they are doing is they are giving some spatial, making some spatial query. So in conditional DTR, they are wanting to divide the query signals, object query signals, into 2 types. One is the content query, and the other is the spatial query. Okay. Content query is to say containing some information for the class information. As spatial query, you can think this as containing some locational information. So because we have to estimate both class information and also the bounding box information, the queries have to be divided into 2. First, having the content information and the other one for the spatial information. And this part is proposed to making the spatial queries. So this is the previous layers output, which is inputted to this another round of the self-protection mechanism. So this is same as the previous key query values. Okay, so we will call that as add, the decoder embedding. But here in this part, we will make, how to say, the new vector, which is called as S. Okay, and this is called as reference point. Okay, so here we are somehow estimating some of the location information. So this is, you can see 2D coordinate embedding. So from the object queries, we are actually estimating the spatial information, which is the x and y coordinate. And then we are actually doing some, so here what we actually estimate is P of Q, which is meaning the positional query, okay? Spatial query or positional query. Okay, so using S, which is the reference point, and using F, which is the decoder previous layers embedding vector, we are estimating P of Q, which is the positional query. Okay, and actually this is how this works. Okay, P in the middle, we estimate P of S by applying this to the S, okay? And also P of S is coming from here, and T is coming from this part. So by applying FFN to F, which is the feed-forward network operation to F vector, we get the T, okay? And then by multiplying these two, F and S, okay, then we get the P of Q, which is the positional query, okay? So that is happening in this part. So even though this is quite complex, okay, so, but I mean, this is how authors of this paper implement this part, okay? Any other variant could be there. So the important thing we have to note here is there are some content query, which is from the F, as partial query coming from S signal, and we are estimating U positional query, by combining two information. And then what we do here is we concatenate. The C means concatenation operation. We concatenate the positional query information and also the content query information coming from the previous layer's output. And why we concatenate both of things is, this is what happened when we add the positional vector with content vector, okay? So this is meaning the content query, and this is the positional query, okay? This is the content key and positional key. If we add this content query and positional query and apply the dot production as in the attention mechanism, then somehow content query and positional queries are mixed, okay? But in the conditional DETR, this is what original DETR does for calculating the attention, and somehow they are mixing the content and positional information. But in the conditional DETR, what they do is rather than adding this content and positional embedding, they are doing concatenation of these two information. And when apply dot product to this concatenated signal, then these two are multiplied, and these two are multiplied, and they are added like this. So because of that, now we can separate the content information and positional information in the conditional detail. Okay, somehow we can retain this content and positional information separately in conditional detail. Okay, so that's why we are having in this architecture we are having concatenation operation rather than the addition operation in the self-attention. Self-attention we are using addition for content and spatial information. But in the cross attention, we are replacing those additions to the concatenation operation to separate content and spatial information. So thanks to this, now the object queries which previously doesn't have any spatial information and doesn't contain any image specific information before, is now containing spatial information of the images. Okay, and because of that, the conditional DETR is now converges faster than the original DETR. Okay, so even with uh, 10 times less number of epochs, uh, the conditional DETR is working properly. Okay, that's the difference made in this conditional DETR. Okay. And so the other variant of this DETR for improving the object queries is the depth DETR. Okay, so this is the original DETR. Their activation of the final, this is visualization of attentions of positional query and positional key values. Okay, and here is the conditional DETRs. And this is the depth DETRs. Okay. So compared to the DETR, this conditional DETR, they are well capturing the positional information about the bounding boxes. So this is not well capturing rigid object. Okay. But here, conditional DETR, they are capturing the objects well better than the original DETR. But that DETR, what they think is the attention of the conditional DETR is still unconcentrated and is more, how to say, sorry about that. So A is the DETR, original DETRs. Okay, this is not unconcentrated and too small or too big attentions. But B is the conditional DETR, and this is more like the Gaussian-like attention, but their object scales are not considered. Okay, but that detail they are explicitly considered the object scales as well. So they are becoming to have sharp attentions. Okay, so that's the motivation for this depth detail. So they are further trying to give more spatial meanings to these object queries. Okay. Previously, in conditional DETR, we are still estimating the bounding box, the coordinate from the object query. So here we are somehow estimating S value from the object query. From the object query, we are estimating S value, which is the coordinate values, okay? But here in that detail, they are explicitly having anchor box representation, which means X and Y, which is center of the boxes, and width and height, which means the box, their width and height. Okay, so instead of estimating the reference point of the bounding boxes, they are explicitly involving the bounding box information in the spatial information. And they are having decoder embeddings as well. So they are now using this anchor box information as the spatial information. And yeah, so there are, iterative decoders are iteratively composed. So they are having multiple anchor boxes. So these anchor boxes are updated using the delta information estimated in the middle. Anyways, their motivation is they are wanting to use explicit bounding box information as the spatial query. Okay. So DETR and conditional DETR, the object queries are high dimensional vector, which is meaningless. they have no direct information between the query and bounding box locations. In conditional DTR, they are estimating bounding box information from the object query. So somehow they are having some relationship, but not direct relationship. But that DTR, they are involving bounding box as the object query information. So they are now having more direct relationship. So they directly use bounding box values as the object queries. And so this is how they are making the object query. And for the self-attention, they are using addition similar to the conditional DTR, but cross-attention, they are using concatenation vector operation to somehow uh, merging the content query and the spatial queries. Okay. And additionally, they are counting the width and height parameters of the bounding boxes. So in the conditional detail, they are only counter their locations, the x and y values, but here they are estimating the width and height of the bounding boxes as well. And also they are using these temperature values to encode the scales of the attentions as well. So that's the difference to the conditional DTR. Anyways, that DTR, here another comparison between DTR, conditional DTR, and depth DTR. Okay, so DTR, the queries are not having any meaningful information, but conditional DTR, from the queries, they are estimating bounding box, their x and y positions. But in that detail, they are explicitly using x and y height and width of the bounding boxes as the object queries. And by doing that, they can secure the faster convergence and more accurate accuracy. Okay. So somehow the high-level motivation of these works are like this. So as I mentioned previously, the object queries object queries by cross-attending the object queries with the enhanced image feature, we have to map them into the bounding box and class information, okay? But previously in object queries, the image information was missing, especially the spatial information was missing. So in conditional DTR and depth DTR, they are wanting to explicitly give the bounding box information for the object query, this part, okay? And make convergence of this overall architecture becoming faster. Okay, so because this part doesn't have any spatial meaning, so mapping this to bounding box information, those that was taking time. That was the reason why it takes more epochs compared to previous fast CNN or other detail variant. But now, by giving more prior information to here, the training is becoming faster. And another, this is last topic for today, maybe. So DND DTR, this is another variant of the DTR. So in the conditional DTR and that DTR, what they want to improve was giving some meaningful information to the object query. So they are focused on improving the decoder and their query information. That's what previous works have done. But DND DTR, they are also pointing out different reasons why the DTR training is slow. So they are saying that slow convergence is caused by bipartite matchings. Unstable bipartite matching happened. Okay, so they are pointing out different reasons why the DTR suffers, requires a lot of epochs. Okay, so they are pointing out the issue is lying on the bipartite matching part. especially in the early stage of the training. Okay. Mm, so that is the problem for detail. The query is unstable. They are matched with the different object in early stages. How to say? We have to from the DTR, we estimate uh, a lot of output. Okay, so previously I mentioned that there are around 300 object queries, and our estimations are same number with the number of object query, and we are having 300 output predictions, their class information and bounding boxes, but we have to choose the best matched predictions with the ground truth and apply actual loads to that best matched output. So that part is called as the bipartite matching. But what they are saying is matching these 300, picking the best output among these 300 predictions that were matched with ground truth, that is becoming unstable in the early stage of the training. That's the problem in DTR. And because of that, it takes a lot of time for training. That's what DTR is insisting. And they are wanting to apply additional denoising loss functions to this DTR training and wanting to stabilize the bipartite matching part. Okay. So, I mean, this is easily applicable, so we will see how easy it is. So, this is the training curve. This is the training epochs, and this is the instability IS measure. The author of this paper is proposing. As I mentioned, there are predictions, around 300 predictions. So all this each denotes one predictions, and ground truths there might be around 10 ground truth object inside the image. And first we have to match these predictions and ground truths. That's what is happening when applying the loss functions when training the DTR. We first match best matched, we have to select best matched prediction to the ground truth and apply the loss function to that predictions only. But what they are saying is, what this graph is suggesting is, uh, when ON matches TM, which means the I's prediction, if I's prediction is matched with this ground truth, M's ground truth, we will, how to say, output M. This function will output M, okay? And if it is not matched with any ground truth, then it means background, then that would be -1, okay? And if I prediction and I -1 prediction, which means I's epoch's prediction and I -1's prediction is not same, uh, then we will count that number. That's the IS measure, okay? This IS measure is, how to say, measuring the instability of the training, which means if this measure is high, then it is meaning that I's epoch and I-1's epoch, uh, their, how to say, matched samples, matched ground truth for each output is not same, which means if IS is high, there are many samples whose output is matched to different ground truths at every epoch. Okay, so this is meaning indeed this is meaning that during the training in each epoch, the ground truth and prediction matches are changing a lot. Okay, so in DETR, depth DETR, and DN DETR, these sample numbers are high in early stages, especially. So this is denoting the training epochs. So in early training epochs, the mismatch between the ground truth and predictions are high, okay, and it is gradually reduced after the epochs, but the speed of this, how to say, the decreasement is important for fast convergence. So DNDETR is proposing some scheme, which is called as denoising scheme, to fast stabilize these unstable matches. Okay, so that's the motivation of this DTR, DNDTR. And maybe for the later part, we will see actually in the later class. Okay, so in the next class, we will learn about DNDTR, their actual schemes to reduce this instability. And also, we will further learn about Dino. Actually, this Dino was one of the most successful DTR variant. I mean, getting merging some of the schemes from that DTR and conditional DTR for improving the queries, and also for improving the instability of the training in the early stage. They are improving some of the schemes of the DNDTR, and what's the state of the art object detector using the transformer. And actually, you remember the grounding deno. We have learned about this grounding deno, and that is marrying this deno architecture with the text signals. That is the grounding deno. So we have learned about that already. So we will also learn about deno, how which kind of schemes were integrated to make it more robust. And then finally, we will learn about RTDTR, which is the real-time DTR. Okay, DTR is still, even though some of the schemes are added to the DTR, still not real-time. But this RT-DTR is making the DTR real-time. So we will see which types of schemes are added to make the DTR real-time. Okay, so we will learn about this next class. Okay, for today we can finish here. Thanks.